11 says a wave pulse is incident on a fixed end as shown. Possible shape of reflected wave pulse is. So this is the wave pulse that is given to us, and this is the fixed end. And after reflection, what could be the possible shape among the four options? Well, we see that the pulse is not symmetrical in the sense that these two dimensions are different, A and B. Now, we know that when reflection happens at a fixed end, the pulse gets inverted. So the first and foremost, the pulse will be definitely inverted by reflection, which leaves us with these two options only. These two cannot be there. 1 and 4 are totally ruled out. Now, after the pulse is reflected, it gets inverted. Now again further, we look at what between these two, what should be the shape, or rather better still, without even looking at this, we can still judge. We can see that when the pulse is reflected like this, okay, let's say this is reflected and it is traveling in this direction. It has been reflected at a fixed end. So obviously this part has got reflected first, right? So that means in the reflected pulse, this dimension will be B and this dimension will be A. So if I look at the options with this information, we can see that only 3 is matching, 4 is ruled out. I repeat again, because this part will reach the fixed end first, this part will be reflecting first of all, and so this part is going to be to the left of this part. Well, applying these two ideas, we can see that the answer is option 3. Let's move to the next question now. The heat transfer is happening through a thick conducting shell whose inner and outer radii have been given as R and 2R respectively. So let's find the expression for the rate of heat transfer to the shell as a whole. Okay, and we of course note that the value of thermal conductivity is not a constant, it's a function of x, the distance from the center of the shell. So let's say we have the inner and outer radius R and 2R. So this is the shell. The inside temperature is given as 0 degrees C, and here the temperature is 100 degrees C. The rate of heat transfer, of course the heat transfer will be from outside to inside, and for that we can use H is equal to minus, the minus term will not come because the heat transfer is happening from outside to inside, and H will be then K, which is C by X, and the area, let's consider any thin shell of radius x and thickness dx. So it is K into the area will be 4 pi x square and dt by dx. So this is the expression, and if we simplify a little bit and do cross multiplication, we have h dx by x equals 4 pi c dt. We integrate, we know that x varies from r to 2r, so it's r, and here it is 2r, the upper limit, and the temperature goes from 0 to 100 degrees C. So we get h, this will be ln x, and putting the limits, it's ln 2, h ln 2 equals 4 pi c into 100. So this is one expression we already have. We have to find x at which temperature is 50 degrees C. So we again use this equation, and the value of h is now known. So the expression is h into dx by x where X goes from R to, let's say, small r. The value of small r is what we have to find, or we could have also called it simply X, it doesn't really matter, is equal to, on the right hand side we have C 4 pi and integral of dt where t goes from 0 to 50 degrees C. Again, doing the integration and putting the value of h, which we already have, we get 4 pi c 100 divided by ln 2, that's the value of h, into ln small r by capital R equals c 4 pi into 50. Let's simplify further. So this 4 pi c cancels, this 50 cancels, and this is 2. What we get is ln of small r by capital R is equal to ln of 2 divided by 2, which can be written as ln of 2 to the power 1 by 2. Now we can see that the value of small r by capital R is clearly 2 to the power 1 by 2 or root 2, and the value of r happens to be then r root 2, which is same as the value of x as given in the question. So our answer to question 12 is option 2. Let's move on to the next question now. Question 13 says, a gas placed in an adiabatic container fitted with an adiabatic piston is compressed by pushing the piston. Then option 1 says mechanical energy of system decreases. Option 2 says internal energy of system get converted into its mechanical energy. Option 3 says mechanical energy provided to system gets converted into internal energy, and option 4 says internal energy of the system remains constant. Well, it's clearly given that the process is adiabatic and some work is done, some work is performed on the gas by compressing the gas by pushing the piston. Well, this being an adiabatic process, we know delta Q is 0. There is no exchange of heat with the surrounding. So delta Q is 0, which means delta U plus work done by the gas is 0. And work done by the gas is negative. This work has been done from outside. So W is negative and delta U is minus of W. So that means this is positive. This minus W is also equal to work done by the external agent, which is compressing the piston. So we can see that by applying the first law of thermodynamics, the internal energy of the gas is increasing, and which is this increase in internal energy is simply coming, and this shows that the mechanical energy provided to the system is converting into internal energy. So option 3 is correct for question 13. Let's move on to the next question now. So option 3 is correct for this question. Let's move on to the next question now. Question 14 says, two parallel plate capacitor of capacitance 40 microfarad are connected in series to a battery of EMF 10 volt as shown. A dielectric material of dielectric constant 4 is inserted between plates of one of the capacitors. Charge flown through the battery is, and the 4 options are given. This is the circuit which is given to us. The value of C is given. So what we do is we analyze the situation before insertion of the dielectric and after insertion of the dielectric. So before insertion of the dielectric, we can see that the effective capacitance will be C by 2 because C and C are in series. So effective capacitance is C by 2, and so initial charge on the capacitors Qi is equal to C by 2 into 10 volt, or which is 5C. volt, right? This is the initial charge on the capacitors. Now, after dielectric is inserted, well, let's say it is inserted in the second capacitor. So, the capacitance now for the second capacitor becomes 4C, because the dielectric constant is 4, and this is C, of course. So, the new C effective will be C into 4C, or 4C square divided by C plus 4C, or 5C, which is 4C by 5. So, the final charge QF is going to be 4C by 5 into 10 volt. So, 4C by 5 into 10, which is 8C. And so, the additional charge that flows to the battery will be 8C minus 5C. We can call it delta Q, the additional charge. Putting the value of C, this is 3 into 40 microfarad. So, this charge will be 120 microcoulomb. And this is clearly matching with option 2. Pretty simple, isn't it? Let's go to the next question now. Question 15 says, 3 concentric metal shells A, B and C have radii A, 2A and 3A respectively. If the charge density on the outer surface of each shell is sigma, then potential of shell C is. Well, the question is clearly from the topic of electrostatics, where potential is also involved, the properties of conductors are also involved. And what I do is, I draw the 3 concentric metal shells A, B and C first and take it from there. So, let's say this is shell A, then this is shell B, and let's say this is shell C. This radius is A, this radius is given as 2A, and this radius is 3A. Now, it also says that the charge density on the outer surface of each shell is sigma. So, if it is sigma here, here also it is sigma, and here also it is sigma. It's clearly given to us in the question. Okay. Now, if we look at it, if the charge on the inner shell is, let's say, QA, then there is induced charge of minus QA on the inner surface of B, right? And similarly, if charge here is QB on the, that means charge on the outer surface of B, if it is QB, then charge on the inner surface of C will also be minus QB. Okay, that much charge will be induced. We know that from the property of conductors, and this we get by applying Gauss law and also considering the fact that the charge at the core of the conductor in the interior of the conductor is always 0 in electrostatic conditions. So, we can see that all this is happening, and here again the charge density on the outer surface of C is also sigma. So, what does it give us? If we want to find potential of C, Vc, let's call it, this will be 1 by 4 pi epsilon naught into QA, which is the charge on the outer surface of A, and there will be charge only on the outer surface of A. I mean, there is no charge on the inner surface of A, divided by this distance is 3A, and then again potential due to this shell of charge will be minus QA by 3A. Similarly, if charge here is QB, so we get QB by 3A, and then again there is minus QB by 3A because of this shell. So effectively, all these layers of charges, the effect is cancelled as far as electric potential is concerned on the outermost shell. And finally, we have charge on the outer surface of C, which will be equal to, let's say, QC and divided by 3A. So all these terms cancel, and what we are left with is 1 by 4 pi epsilon naught QC by 3A. Now we can see that QC, the value of QC will be 4 pi into the radius square, which is 3A whole square or 9A square sigma divided by 3A. And further on simplification, this comes out to be equal to 3A sigma upon epsilon naught. And if I look at the options, it's matching with option 2. So option 2 is correct. Let's move on to the next question now.